We just finished covering Chapter 29, which deals with thermochemistry, information that we learned back in Gen Chem 1. We're going to take that information now and move on to Chapter 35, which we're going to apply some of that information we learned in Chapter 29. We're going to start off with the second law of thermodynamics, which addresses the questions about spontaneity in terms of the quantity called entropy. Entropy, which is symbolized with a capital S, is a thermodynamic quantity that is a measure of the randomness or disorder of a system. Now, this is a simple version of the definition of entropy. There's a more complex one which we're going to talk about later. Entropy is what's more complex than what we're going to cover in this class. We're going to focus on just the randomness or disorder of a system when we're talking about entropy in this class. The SI unit of entropy is joules per Kelvin, and like enthalpy is a state function, which basically means we can do similar calculations that we did with delta H, we can do that with S, okay, entropy, which means the law of summations, Hess's law, those type of things. We can do calculations with entropy the same way we did our enthalpy calculations. You might recall we drew these potential energy diagrams back at the beginning of this chapter 29, where we said if reactants are species of high energy, then they're very unstable and very reactive. They want to get to a state of low energy. Well, to do that, since they're in control of it, they got excess of energy, they can release that energy. Okay, if we release energy, we say it's an exothermic process. And since it's in control of that happening, we say that's a spontaneous reaction. On the other side of the coin, we could have reactants that are very low energy, very stable, unreactive. Well, to get it to a higher energy state of product, then it's going to have to absorb energy from somewhere else. We refer to that as an endothermic process. And since it has to get energy from somewhere else, we say it's a non-spontaneous reaction. But we also stated that heat is not the total picture when determining if a reaction is spontaneous or not. There are other processes involved that decide if the entire reaction is spontaneous or not. Let's look at case of a soluble salt. Most soluble salts dissolve in water spontaneously. However, most soluble salts dissolve by an endothermic process. Okay, so most salts dissolve spontaneously. However, most soluble salts dissolve spontaneously. However, most soluble salts dissolve by an endothermic process. What does that mean? Let's look at an example. Ammonia nitrate breaks up into ammonia ions and nitrate ions, and it's an endothermic process. It absorbs 28.1 kilojoules of energy. We stated earlier that to break bonds, if I want to break that ammonia nitrate bond, that ionic bond, it will have to absorb energy to make that happen. Then it'll break up into its ions. We said when it forms bonds, it releases energy. Well, in this process, there's no bonds being formed, so all we're doing is absorbing energy to break the bonds. There's no energy being released to form any compounds. So we're saying here is we're absorbing energy, and it's a spontaneous process, so it must be going to a lower energy state. That seems contradictory. How can I absorb energy yet get to a lower energy state? So there has to be something else going on that we're missing. There has to be another piece to the puzzle here to allow this reaction to be spontaneous. And it does have another piece, which is this statement right here. There is an increase in molecular disorder or randomness of the system. Okay, this particular reaction going from ammonia nitrate as a solid to ammonia ions and nitrate ions, there's an increase in molecular disorder or randomness of the system. Basically, we're increasing in disorder, which is energy associated with order or disorder of a system. Okay, so we're going from a solid, which is a highly ordered system, to aqueous ions, which is a less ordered system. And what there is a less energy associated with that disordered system compared to that ordered system of a solid. Just to bring up my point of energy associated with order, let's say you went to your friend's house. In your friend's house, you walked in the room and it's all nice and neat. Everything's in its place. You have a bookshelf. All the books are alphabetized. Okay, you look in the closet. All the clothes are arranged by color coded. Okay, you look on their bed and they got stuffed animals and they're all alphabetized as it goes around. How much energy does it take to keep that room in that type of order? A lot. Okay, if you go home to your house and you look and you don't even put any books on the bookshelf. All the books are on the floor. You don't hang your clothes up. You just throw them on the ground. You don't even make a bed, so there's no bedspread, no animals on it, no nothing. It's just total sheets all over the place. How much energy does it take to keep your room like that? Not very much. Okay, so there's energy associated with order. Okay, so when we're talking about going from a solid to a liquid to a gas, etc., there's order associated with those states. Solids tend to be very high order, or another way of looking at it, low disorder, and there's a high energy associated with solids. Solids tend to be a very ordered system. Okay, there's a pattern to how the molecules are put together. Okay, so it's a very high energy system. Okay, so we're talking about low disorder, or opposite of that would be high order, and we're talking about high energy. Liquids are in between, okay, because the molecules are free to move the total volume of that liquid, okay, and gases are at the other extreme, okay. Gases tend to be molecules move around and fill out the entire container, right, to fill out the whole container, okay. So they basically will spread out and try to get as far apart as possible. What happens here is that we have a very high disorder system and a low order system, which means I have low energy. Okay. So in this particular example, what has happened is that we went from a solid to aqueous ions. So there was a decrease in energy from going from a highly ordered solid system to an aqueous ion system. Okay. That energy was enough energy to overcome the amount that we needed to absorb to break the bond. Now, does this happen for everything? No, everything's not soluble, right? So only certain salts are soluble. So the energy associated with it has to be things that are very large in size or very low in charge. That way that bond's not very strong. So on the solubility rules, all those solubility rules we learned are all based on size and charge, and all those things we said are soluble tend to be very large, bulky species or things with very low charge. Things with very high charges, like +2 or +3, don't tend to be soluble, okay? Because we don't have enough energy to overcome that change from a solid to an aqueous ion. It doesn't have enough energy to overcome the strength of bond energy I need to overcome that bond. So here's the technical definition of entropy. Entropy is a thermodynamic quantity that is a measure of how dispersed the energy of a system is among the different possible ways that system can contain energy. Typically, it's in the units of joules per Kelvin. So it's very complex. There's a large possibility of sources of energy. We're just going to narrow it down for our purposes. Okay? One example. Okay? We're going to narrow it down to one example of entropy of what we're going to follow. We're going to follow the amount of molecular disorder or randomness in the system. Okay? So we're going to do it from the point of view of disorder. Okay? For where we follow an entropy. An increase in entropy basically means, in our purposes, is an increase in disorder in the system, okay, which also means that the energy decreases. So we're saying if we increase in entropy, then our total energy of our system will decrease. Gases tend to have a high disorder, therefore it has a low energy. Solids tend to have a low disorder, therefore high energy. Liquids are in between. We typically follow the change in entropy in the system, so we treat it as a state property, and we measure it as we do with delta H's. We can do a delta S, which is our final entropy minus our initial entropy. So a plus delta S, meaning an increase in entropy, means there's an increase in disorder, which means a decrease in internal energy. If we have a decrease in entropy, meaning a decrease in disorder, it will be a positive, an increase in internal energy. Which gets us to the second law of thermodynamics. Which states The second law of thermodynamics states that the total entropy of the system and its surroundings increases for a spontaneous reaction, a spontaneous process. Because more disorder is lower energy, it favors a spontaneous reaction. Okay? More disorder means lower energy, which means favors a spontaneous reaction. The tendency of a system to increase its entropy is the second most important factor in determining the spontaneity of a chemical or physical change, in addition to that enthalpy. Okay, so we basically need to look at both your delta H and your delta S to figure out what's happening in a reaction, determine if the overall process is spontaneous or non-spontaneous. So, for a spontaneous process, one which the system is going to lower energy, okay, and that's what we say is spontaneous, it's favored by an exothermic process. So if we're talking about an exothermic process releasing energy in negative delta H, that favors a spontaneous process. If we're talking about a process that's increasing in disorder, meaning a positive delta S, that favors a spontaneous process. So these two processes favor a spontaneous reaction, exothermic increase in disorder. A non-spontaneous process, meaning the system going to a higher energy state, is favored by an endothermic process, meaning a plus delta H. So basically, if it's absorbing energy from the surroundings, then it's going to be a non-spontaneous process based on just heat. If that system is decreasing in disorder, which is a negative delta S, it favors a non-spontaneous process. So an endothermic process or a decrease in disorder favors a non-spontaneous process. Now, if we have an exothermic process and we have an increase in disorder, then we know it's a spontaneous reaction. If we have an endothermic process or a decrease in disorder, that favors a non-spontaneous process. Now, what if we have contradiction? We have something, say, as an endothermic process, which favors a non-spontaneous process, and we increase in the disorder, which favors a spontaneous process. What happens in that case scenario? Is it spontaneous or non-spontaneous? Well, it goes back to the example we just talked about, where we said, I don't need both of them to be true. One of them is going to be bigger than the other one is going to dictate the overall process. Okay? For the salt dissolving, that was an endothermic process. But going from a solid to the aqueous ions, that was a case where it was increasing in disorder. The increase in disorder of the ions, the increase in disorder of the process was larger in energy than the amount I needed to absorb to break the bond. Therefore, the overall process was a spontaneous reaction. Okay, so basically, the larger term will dictate the overall process, and we talk more about how those terms are related and determining which one's larger later on. The third law of thermodynamics states that the entropy of all perfect crystalline substances approaches zero as the temperature approaches absolute zero, meaning on the Kelvin scale. Remember, there's no negative temperatures on the Kelvin scale. As the temperature is raised, the substance becomes more disordered as it absorbs heat and becomes a liquid and a gas, where entropy basically is greater than zero. So an important factor here is we know that entropy increases as temperature increases. Okay, so as we increase the temperature, we're changing states, and we also increase in our entropy term. The entropy of a substance is determined by measuring how much heat is required to change its temperature per Kelvin degree. So we have zero entropy as a species is a solid, okay, at 0 Kelvin. And that value will increase, that entropy value will increase as it goes to a liquid, as it goes to a gas. Okay, so we start off at 0 entropy, at 0 Kelvin, and go up from there. The standard entropy of a substance or ion, also called the absolute entropy, S superscript S, is the entropy value for the standard state of the species. This is very similar to your delta HFs. Okay, remember we talked about the standard before. Since it's a standard, we give it that little superscript 0, which means we're at 25 degrees C. Okay, 1 atmosphere, 1 molarity for substances. Okay. However, Notice there's no delta in front of the S. Since this is an absolute value based on that third law of thermodynamics, okay, there's no delta in front of that. This is absolute. It's based on 0 Kelvin, and we go up from there. 0 entropy at 0 Kelvin, and it goes from that value. Remember, on the delta HF stuff, that was a relative scale. It was relative based to everything we said at room temperature being 0 delta HF. So oxygen, O2. Room elemental oxygen, O2 is 0 delta HF. However, the entropy of that's going to be some numeric value because it's not on a relative scale, it's on an absolute scale. That little superscript means standard state, which implies 25 degrees C, 1 atmosphere pressure, and 1 molarity for dissolved substances. As I just mentioned, basically what we're saying here is the elements have non-zero values for entropy because it's an absolute scale. Unlike the standard enthalpies of formations, which by convention are 0 because it's a relative scale. So things like I said, oxygen, iron solid, nitrogen gas, all those are 0 delta HFs. However, with entropy, they will have some numeric value because it's on an absolute scale based on that third law of thermodynamics. This is also why we tend to use the symbol S with a superscript 0 rather than delta S. We don't use the delta S as the symbol when we're looking in tables, okay? For tables for your delta HFs, you get delta H. For your entropy, this is going to be S, okay? There's no delta in it. That doesn't mean I can't calculate delta species. I can do the delta S. That would be my S final minus my S initial, okay? So I can calculate my change in it, but it's not a change value as on tables. It's a relative, absolute value. So we tend to write it as a capital S, no delta S. All right, we can calculate the enthalpy change for a reaction, that delta S, by taking the summations of my S of my products. Okay, remember it's S, not delta S. Take into account my number of moles and minus my summation of my S, my entropy of my reactants, take into account my number of moles. Same way we did delta HF. Exact same way, except the formula we have S instead of delta S. Okay, so summation of your entropy products minus your summations of your entropy reactions, accounting for the number of moles. We can calculate. We also can do a judgment call and make a prediction of what the sign is going to be by looking at the reaction. So even without knowing the values of entropy of the substances, we can sometimes predict the sign of our delta S of the reaction. The entropy usually increases in the following situations. Okay, a reaction where if a molecule is broken into 2 or more molecules, the delta S is going to increase. Okay, what we're doing is coming from 1 molecule to 2 molecules, so you're introducing more chaos, more disorder into the system. It's kind of like saying I have a crowded room and I add more people. What's going to happen? It's going to get more disorder, more chaos. Okay, so in essence, it's talking about a molecule AB breaking up into A and B are broken up into more species. Okay, so therefore I got more disorder in the system. It's an increase in my overall disorder, a positive delta S. If I have a reaction in which there is an increase in the moles of gas, I'm going for something that's ordered to less order, okay, or more disorder. I'm increasing more disorder in the system by doing such. Example, A gas going to B gas plus C gas. I'm introducing more gaseous molecules. Okay, I'm increasing. That's going to be a positive delta S. Okay, reaction with an increase in the number of moles of gas, I'm also increasing more disorder. We're also going to talk about changes in state. Okay, a process in which a solid changes to a liquid or gas, or a liquid changes to a gas, that's an increase in disorder. So I have a solid and it breaks up into a liquid or gas or a combination. That's an increase in disorder. I'm talking about a liquid. It goes and changes to a gas. That's an increase in disorder. Okay, these are all examples of increases in disorder. So I basically can look at the reaction and decide what's happening to my disorder to see if I'm going to have a positive delta S or a negative delta S. Okay, let's see if we can predict the delta S for some reactions. Okay, and we're also going to determine if it's a spontaneous or non-spontaneous reaction based only on entropy. Okay, so based only on entropy, we're going to decide if it's a spontaneous or non-spontaneous reaction. We're basically neglecting the enthalpy term, okay? Remember, that doesn't give me the whole picture, because just because I say it's spontaneous or non-spontaneous based on entropy, enthalpy may be enough to switch the opposite process, okay? But for this practice, for this exercise, we're just going to look at entropy to decide if it's spontaneous or non-spontaneous. Let's look at a reaction. I got ethylene plus bromine gives me ethylene dibromide. Okay, so we're going to look at this and see what's happening. It's going from gaseous molecules to liquid molecules, which is the indication it's going from a highly disordered system to a less disordered system. So that's an increase or decrease in disorder. We're also going to look at it in terms of number of molecules. It's going from 2 moles to 1 mole. So it's going from something that's more disordered to less disorder. So therefore, we once again talking about an increase in a decrease in amount of disorder. And if we're talking about a decrease in amount of disorder, then we're basically talking about a favoring a non-spontaneous reaction. So it's going from gases to a liquid, as well as going from 2 moles to 1 mole. So therefore, it's a decrease in disorder, or negative delta S. Therefore, based solely on entropy, we say that it's a non-spontaneous reaction. All right, let's look at ethane plus oxygen gives me carbon dioxide and water. In this case, we're talking about everything being gas, so there's no change there. But there is a change in the number of moles of gas. It's going from 9 moles of gas. Okay, we got 9 moles of gas to 10 moles of gas. So what we're doing is we're having an increase in the number of moles of gas, which means we're increasing more disorder in the system. So therefore, since I'm increasing in disorder, that means it's going to be a positive delta S, and that favors a spontaneous reaction based solely on just the entropy. So we're going from 9 moles of gas to 10 moles of gas, therefore it's an increase in disorder, which is a positive delta S. So spontaneous based solely on just an entropy term. Okay, I got glucose breaking up into ethanol and carbon dioxide. I'm coming from solid to liquids and gases, so I'm coming from a highly ordered system to a less ordered system, or highly low disorder to more disorder. Also, you can look at this as being decomposed, going from 1 molecule to 4 molecules. That's more disorder. So in both cases, we're increasing in disorder, or a positive delta S. Therefore, we're looking at a spontaneous reaction based solely on entropy. So solid going to liquid gas, basically decomposing into more molecules, increase in disorder, or a positive delta S, and spontaneous based on just entropy. Homework. Okay, homework 47. Ask you questions dealing with entropy to see if you can determine if there's an increase or decrease in entropy.